Hi everyone, this is Sahara and today we're going to dive deep into Traveling Salesman Problem using dynamic programming. Now, if you're here on an emergency right before your exam or the deadline for your homework, I have actually put a timeline to where I start solving an actual example so you can take care of your problem. But if you're here to learn about the time complexity, what the actual problem is, and basically learn it from ground up, I suggest you watch this video alongside me. Okay, let's get started. Okay, as usual, we are going to break up this video into three main parts. First, what is the traveling salesman problem altogether? Secondly, why do we need dynamic programming to solve this problem? And third, to solve an example together. Okay, let's talk about what is a traveling salesman problem. We have a graph, and we know it's a complete graph because everything is connected to everything, is a bidirectional graph. And we are given a distance matrix. This basically tells us the cost of going from each vertex to the other vertex. So from 1 to 2, 1 to 3, 3 to 1, 3 to 2, 3 to 4. And because it's bidirectional, we can go backward as well. So it's not just 1 to 4, we can also do 4 to 1. You may have heard of Hamiltonian cycle problem. In this problem, we are searching to see if there is a path that connects all of our vertexes together. Now, for a traveling salesman problem, we know that the Hamiltonian cycle is already met. There is actually multiple Hamiltonian cycles. Everything is connected to everything. Our question is, what would be the minimum cost to get from one particular vertex, visit every single vertex only once, and come back to our vertex? This problem, and in general, graph problems have a lot of real-life applications. I'll give you a few examples. If you're trying to do path planning for shipping, every one of these vertexes can be your different cities, and you can try and see what would be the minimal way of getting from one city if you have to visit every city on your way and then come back to your city. A lot of flight paths can use this algorithm. You can plan what would be the minimal cost of fuel or time to be able to make all your stops and come back to destination. Basically, anytime that you have to visit certain number of destinations, but you have multiple ways of visiting them, this is a useful graph. If by any chance you have watched my multi-stage graph problem, if not, I'll link it here. That problem is a little bit different. We were just trying to get from our start to destination as optimally as possible, and we could skip a bunch of nodes in between. In this case, the condition is we have to visit every single node. Now, let's see, why do we need dynamic programming to solve this problem? If you are given this problem, what would be your intuition to solve it? First naive way might come to mind, and that would be doing it the brute force way. And let's kind of see what would be the time complexity of that. Let's say it's a salesman visiting n number of cities. If we start from node 1 in this example, we have n minus 1 nodes to explore. Now, we need all the possible permutations of these n minus 1 nodes. And you should know the formula of permutation is whatever number we have, factorial. So if we have, let's say, 1, 2, 3, 4, then you want to do 1, 3, 2, 4, 1, 4, 2, 3, or 1, 4, 3, 2. So this is what permutation means. Now, to be able to get the cost of each one of these ways that we are trying to do is we have to travel through this whole way and calculate our cost. What's the cost of 1 to 2, 2 to 3, 3 to 4, and then of course we go back to our destination. What is the length of this sequence? The length of this sequence is obviously n. So for each permutation, I have to travel n times because there's n elements. So this whole thing, n minus factorial times n, is actually equal to n factorial. So the big O of doing the traveling salesman problem using brute force is n factorial, and n factorial is horrendous. So we're trying to see if we can do a little bit better with dynamic programming. Okay, we have arrived at my favorite part of the video, and that's to solve an actual example. Before we start, I have written the dynamic programming formula, and I want to just go over the notation a little bit. We start with the cost of I and V. So let's see, what is this cost? This cost is the minimal cost of starting from a particular vertex, visiting all the remaining vertexes, and then going back to that particular vertex. And what is I? I is basically a starting vertex. And what is V? V is actually not one thing. V is the set of vertexes excluding the vertex I. Okay, so the cost of I and V equals to J being a member of V, meaning J is going to be one of the vertexes that we had in our set of V, and the cost is going to be minimum of D of I and J. So what is D? This D is actually the distance between vertex I, or a starting vertex, and vertex J, which is going to be inside our V set. This distance is given to us in our distance matrix. So we have this number, and this is not to be confused with the cost. Okay, plus cost of J, J we have picked over here, and the set of vertexes minus this vertex J. So we have to take our vertex J out of it and get this cost. Now we have one condition. If the set of vertexes becomes an empty set, meaning we have no more vertexes, the cost of any vertex and the empty set is going to be equaling to the distance of that particular vertex and our starting point. You should have a little bit of intuition as to what this means. You see here, I am removing the J's progressively from my set of vertexes. So at some point, I am going to be left with no vertexes. So what does that mean? That means I started from my starting point, I visited all of my vertexes, I removed every single vertex that I saw from my list, and now I have no more vertexes to visit. So what happens when I have nothing else to visit? I have to go back to my starting vertex per the problem definition. As an example, I've started from vertex 1 and I have gone to vertex 3 and 4 and now I'm on vertex 2. So I have visited all my vertexes. So what do I need to do when I'm here? I have to go back to my destination. So I go from 2 to 1. So that's basically what that statement means. You're going to kind of see it in action once I start solving the example. Okay, let's start with cost of 1, which is our starting point, and V. What should V be? V should be the set of all of our vertexes excluding whichever vertex is this one. In this case, this vertex is 1. So the set of vertexes are going to be 2, 3, and 4 equals to minimum of. Let's see what J can take in this case. J can take whatever is inside my V set. So J can be 2, 3, and 4. J equals to 2. And then we have J equal to 3 and J equal to 4. Let's start here. J equal to 2. It's D of I and J. I is 1, J is 2, plus cost of J, which is 2, and set, which is 2, 3, and 4. So that's 2, 3, and 4 minus vertex J, which is 2. Let's simplify this there. Cost of 2, and if I take 2 out of this set, it's 3 and 4. Okay, D of 1 and 2. 1 and 2. That's 14. Plus cost of 2 and 3 and 4. Do I have this number? No. I need to expand this. So I come here. Cost of 2 and 3 and 4. What can J take here? J can take 3, J can take 4. Okay, let's do it for J equal to 3 first. That is equal to D of I, which is 2, and J, which is 3, plus cost of J, which is 3, and V, which is 3 and 4, minus vertex J, which is 3. D of 2 and 3, 2 and 3, that's 12, plus cost of 3, and if we take vertex 3 out of this set, is going to be 4. Okay, now I have cost of 3 and 4. You should not assume that cost of 3 and 4 is equal to distance of 3 and 4 because we only have one vertex here. These two are not the same. This is a distance matrix. This is a cost matrix. We still have to expand this. Cost of 3 and vertex 4. That's equal to minimum of. What can J take here? J can take only 4. J equal to 4. That's equal to D of I and J, 3 and 4, plus cost of j, which is 4, and v, which is also 4, minus vertex j, which is 4. Let's see what we get here. This is going to be cost of 4, and if I take 4 out of a set that only has a 4 in it, what it becomes? It becomes an empty set. Now I have a condition that has been met. Here, my set has become empty. So I have a cost of some vertex and an empty set. So now I can say in this case only, this cost is equal to d of 4 and my starting vertex. This is the only time I can draw the conclusion of equality. So d of 3 and 4, 3 and 4, that's 6, plus d of 4 and 1, 4 and 1, that's 7. So this whole thing is 13. So this term is 13. I got this term from here. Now, which j gave me this 13? J equal to 4. I need to somewhere keep track of this j, because later on I need to know which vertexes did I traverse to get the minimum number. 12 plus 13 is going to be 25. Which j gave me 25? J equal to 4. Now, find the number for j equal to 4. J equal to 4. That's d of I, which is 2, and j, which is 4, plus cost of j, which is 4, and v, which is 3 and 4, minus 4. D of 2 and 4, 2 and 4 is 8, plus cost of 4, and if we take 4 out of this set, is going to be 3. Now let's calculate this cost again. So cost of 4 and 3 equals to minimum of j can be set of 3, so j can only be 3. So that's d of I is 4, j is 3, plus cost of j, which is 3, and v, which is also 3, minus vertex j, which is 3. So we know this is empty set, so cost of 3 and empty set. 3 and empty set is equal to 3 and 1. So d of 4 and 3, 4 and 3, that's 6, plus d of 3 and 1, 3 and 1, that's 9. So this whole thing is 15. So 8 plus 15 is 23. Which j gave me this? J equal to 3. Now, which one is the minimum? This one is obviously the minimum, the 23. So I have to take the 23 and put it here for this term. We did all these calculations to get this term. Now, which j gave me the 23? This j did. So we kept track of what j gave me the 15, and then we have to know which j gave me the 23. So j equal to 4. I don't need to know anything about this j3 because this did not give me the minimum. So no need to keep track of that. So let's see what we get here. 14 plus 23 is 37. Now, just so that I can keep track of my vertexes, I put over here 37 came from 4 and 3. Okay, and write them to this order, 4 first, 3 later, because you're gonna see this is how our algorithm is gonna flow. Okay, let's calculate j equal to 3. So d of I, which is 1, and j, which is 3, plus cost of j, which is 3, and my set of vertexes 2, 3, and 4, minus my vertex j, which is 3. Okay, d of 1 and 3, 1 and 3 is 9, plus cost of 3, and if I take 3 out of this, I'm gonna be left with 2 and 4. Let's calculate this cost. So that's cost of 3 and 2 and 4 is equal to minimum of, what can j take? J can take either 2 or it can take 4. So let's do it for j equal to 2 first. So that's d of I, which is 3, and j, which is 2, plus cost of j, which is 2, and our set of vertexes, which are 2 and 4, minus j, which is 2. So d of 3 and 2 is 12 plus cost of 2, and if I take 2 out of this, I'm going to be left with 4. Let's get this. So that's cost of 2 and 4 is equal to minimum of, what can j be? J can only be 4. So j is equal to 4. D of I is 2 and j is 4, plus cost of j, which is 4, and v, which is 4, minus vertex j, which is 4. This becomes cost of 4, and if I take 4 out of the set of 4, an empty set, which equals to d of 4 and 1. D of 2 and 4 is 8, plus d of 4 and 1 is 7. So this whole thing is 15. So let's put this 15 here. 12 plus 15 is 27, which j gave me the 27, j equal to 4. And let's calculate j equal to 4 now. J equal to 4. So that's d of I, which is 3, and j, which is 4, plus cost of j, which is 4, and our set of vertexes, which are 2 and 4, minus 4. So d of 3 and 4, that's 6, plus cost of 4 and 2. Let's calculate this. So that's cost of 4 and 2 equal to minimum of, what can j take? Only 2. So j equal to 2. D of I and j, so 4 and 2, plus cost of j and 2, minus vertex j. D of 4 and 2 is 8, plus cost of 2, and we know this is going to be an empty set. This we know is equal to d of 2 and 1. D of 2 and 1 is 14. 8 plus 14 is 22. This whole thing is going to be 22. So 6 plus 22 is 28. Which j gave me this 28? J equal to 2. Okay, so the minimum of the 2 is 27 for this term. So 27 plus 9 is equal to 36. Okay, now let's look at our j's. We brought the j equal to 4 when we were doing our calculations. And then the next j we need is j equal to 2. So 2 and 4 need to be written here. Because we're doing a bottom-up approach, whatever number you're getting first needs to come last. So I got this 27 because of a calculation I did here earlier, which I have erased. And then I got the 2 because of this. So 2 comes before 4. Let's do it for the last one, which is j equal to 4. So d of I, which is 1, and j, which is 4, plus cost of j, which is 4, and our set of vertexes, which are 2, 3, and 4, minus vertex 4. So we know d of 1 and 4 is equal to 7, plus cost of 4, and if we take 4 out of this group, is going to be vertexes 2 and 3. Let's get the answer to this. So that's cost of 4 and 2 and 3 is equal to minimum of, what can j take? J can take 2, j can take 3. For j equal to 2, that would be d of I, which is 4, and j, which is 2, plus cost of j, which is 2, and our vertexes 2 and 3, minus vertex j, which is 2. So d of 4 and 2 is 8, plus cost of 2, and if we take 2, this is the 2, out of this equation, we're going to be left with 3. Let's get that number. Cost of 2 and vertex 3 is equal to minimum of, what can j take? J can only be 3. So j equal to 3. So that's d of I, which is 2, and j, which is 3, plus cost of j, which is 3, and our set of vertexes minus vertex j, which is 3. So that's empty set. So d of 2 and 3, we have a 12 there, plus cost of 3 and empty set. This is equal to 3 and 1. So 3 and 1 is 9. 12 plus 9 is equal to 21. So this whole thing is 21. 21 plus 8 is 29. 29. J3 gave us this 29. Now J equal to 3. J equal to 3 is D of I, which is 4, and J, which is 3, plus cost of J, which is 3, and our set of vertices, which are 2 and 3, minus vertex J, which is 3. D of 4 and 3. 4 and 3 is 6, plus cost of 3, and if I take 3 out of this equation, so let's calculate that. Cost of 3 and 2 equal to minimum of, what can J take? J can only be 2. So that's J equal to 2, equal to D of I is 3, and J is 2, plus cost of J, which is 2, and our set of vertices, which are 2, minus vertex J, which is 2. The distance of 3 and 2 is 12, plus cost of 2 and empty set. This is equal to distance of 2 and 1. Distance of 2 and 1 is 14. 12 plus 14, 26. So this thing is 26, and 6 plus 26 is 32, which J gave us that 32, J equal to 2. Now, between these two, I have to take the minimum. Obviously, the minimum is 29. So this is 29. 7 plus 29 is going to be 36. Now, let's transfer our J's. We had J3 here, and we have J2 after it. Now, I'm going to clean up this a little bit and then go over what just happened. All right, we need to get the minimum of these three to get the final answer for the cost of our traveling salesman starting from vertex 1. As you can see, the minimum of these three numbers is obviously 36, and we accidentally have 236. Now, I don't solve my examples ahead of time. I just like to solve them alongside with you guys, so I didn't know we're gonna have equal numbers over here, but that's good. We get to practice it two different ways. If you encounter a situation like this, that does not mean your answer is incorrect. That just means you have two different ways of achieving an optimal or minimum result. Normally, if you would only see one of them being minimum, that meant you only have one answer. Okay. So if you want to know what's the minimum cost of starting from vertex 1, visiting every single vertex, and then coming back to vertex 1, the minimum cost is 36. Now, how do I get that 36? This is why I was keeping track of which J's gave me the minimum. This is going to be helpful now. Now, I told you, because we're doing bottom-up approach, whichever number you're getting here needs to be the last number. So now I have my whole table. I know here J is 3, right? So 3 goes on top of these, and here J is 4. So 4 goes on top of this. So I have two ways to get the minimum. I'm gonna start from vertex 1, go to vertex 3, I've written it here. Then I'm gonna go to vertex 2, then I'm gonna go to vertex 4, and then I'm gonna go back to vertex 1. Or I can start from vertex 1, go to vertex 4, go to vertex 2, go to vertex 3, and then go to vertex 1. Okay, so if I take these two ways, I'm gonna get the minimal answer. Let's see if this answer is correct. Going from 1 to 3, that's gonna be 9, plus going from 3 to 2, 3 to 2, that's 12, plus 2 to 4, 2 to 4, that's 8, plus 4 to 1, 4 to 1, that's 7. So this whole thing is 36. Here 1 to 4, 1 to 4 is 7, plus 4 to 2 is 8, plus 2 to 3 is 12, plus 3 to 1, which is 9. So that's 36. Very good. They both end up at 36. So we have our final answer and our final way of going from vertex 1 to all of our vertexes and end up at the minimal cost. All right, next we're going to be talking about the time and the space complexity. First thing I want to talk about is that the traveling salesman problem is actually a NP hard problem. If you haven't studied NP hard and complete and things like that, in simple terms, it means that we still do not have a solution that can solve the traveling salesman problem in a polynomial time complexity. If you remember from a lot of other dynamic programming problems that I've been solving, a lot of time we would achieve an order of n by n, let's say in a knapsack problem, or n cube in matrix multiplication problem. So those are really, really good time complexity and space complexities. But for traveling salesman, unfortunately, we still do not have a polynomial answer. The answer to this one you're going to see in a little bit is actually exponential, which basically makes this particular problem NP hard. So I'm going to write what the time complexity is, and then I'm going to explain it. So the time complexity is actually O 2 to the power of n times n to the power of 2. Okay, let's talk about the 2 to the power of n first. This comes from bitmasking. Here you're only going to see one subset of my vertexes, right? So 2, 3, and 4. But I did calculate all of my subsets. Remember, we had the 3 and 4, 2 and 3. All of them were calculated as I was getting all these numbers from a bottom-up approach. So how many different subsets, including the empty set, can you make from a set with n variations? You should know that formula, if you don't know, is 2 to the power of n. So imagine we have 4 vertices. So let's say we can make something like 1, 0, 1, 0, 0. So that means include vertex 1, don't include vertex 2, include vertex 3, don't include vertex 4. Or I can do 0, 0, 0, 1. That means don't include vertex 1, 2, and 3, but include vertex 4. So for each one of my n vertexes, I have binary choice. Include, not include. So that's where 2 to the power of n comes to the picture. Now, let's talk about n to the power of 2. We had to expand our subsets such that we get to a point that each one of my vertexes had the opportunity to be the last vertex. Remember when this condition was achieved, I had a vertex plus an empty set. What did that mean? That meant that particular vertex was my last vertex, right? I visited everything, I had nothing else to visit, so I had to go back home. So I have to give opportunity to every one of my vertexes to become the last vertex so that I can make sure I have done all the calculation. So that stands for one of our n's. So I know I have 2 to the power of n subsets, and I know that every single vertex has to experience being the last vertex. Okay, where does the other n comes from? In the case of the last vertex that I get to, let's say I get to vertex 3, I need to examine all the vertexes that came prior to that vertex. So in actuality, if I'm already at vertex 3, I have n minus 1 vertexes left to examine to see all the combinations of those vertexes coming before my vertex 3 to see which one gives me the minimum. We know in a big O notation, n minus 1 basically is equal to n. We don't care about the constant. So this is n to the power of 2. So that is how we get our big O of 2 to the power of n, n to the power of 2. Unfortunately, in this case, we couldn't achieve a polynomial answer, even with dynamic programming. However, this is still better than the n factorial because we have a 2 to the power of n. N factorial is like the worst. Now let's talk about the space complexity. The space complexity is 2 to the power of n times n. Why 2 to the power of n? For the exact reason that the time complexity was that we have to explore every single subset of our vertexes, and we have to keep those because we're going to have to refer back to those numbers to be able to get to this final number. And this n basically stands for every single one of our vertexes being given the opportunity to serve as our last vertex such that we can go from there to home. Okay, now you should have everything you need to be able to solve your traveling salesman problems. You know how to calculate the minimal costs, you know how to trace your algorithm to know which vertexes you went through. You also understand what the time complexity and the space complexity is. As always, there is nothing better to learn than to actually solve an example on your own. So that's a segue to your homework. I have prepared a a new distance matrix, and I want you guys to get the minimal cost of traveling from vertex 1 to all the vertexes and then come back to 1. And if you want to be really proactive, also let me know which vertexes did you have to travel to get to that final minimal number. Put your answers in the comment down below so I can read them all. I hope you enjoyed this video, and I'll see you on another one. Bye bye. Don't forget to like, subscribe, and hit the bell button.